SwayamPrabha. Digital India. Educated India.
The inside area of this contour is usually filled with a larger diameter radius of the laser beam, and the outer boundary was scanned with a smaller diameter laser beam, so that you can get a small bead width at the periphery and center, and the inside area can be filled quickly. So of course CW is directly proportional to omega naught. Also CW is proportional to the square root of the cure depth, means CW is directly proportional to the root over CD, meaning to say if CD will increase, then CW will also increase, and it is obvious, because to increase CD we need to give more energy, more Emax, and as we are giving more Emax, of course the energy available on the top surface will also be more, and hence you will have larger bead width. However, it can be obviously seen that by increasing the energy, CD will increase faster as compared to CW. Of course, when the CD is greater than dP and less than 4 dP, that is the linear portion of the curve, we have seen that. In that region, if I put this range, what will be the range for CW? In that case, in this inequality, you put the value of CD from here to here, and as a result you will get this expression. This expression says CW by 2 omega naught will be greater than 1 upon root 2 and will be less than root 2. This will be the range for this particular ratio. Now let us try to find out an expression for the velocity of the laser beam. So we have already seen Emax will be given by root over 2 by pi P naught Vx by omega naught, and also we have seen CD equals to dP ln Emax divided by EC, and hence as a result what you have, you can easily find out Emax from this expression as well. Emax will be equals to EC exponential CD by dP. That is what written here. Now if I eliminate Emax from this equation and this equation, as a result you will have the expression for Vx from here that will be independent of Emax. So the velocity Vx will be equals to root over 2 by pi V naught by omega naught 1 upon EC into exponential minus CD by dP. So one can observe from here that the laser scan velocity is directly proportional to the laser power. Of course, if laser power is increasing, then I can increase the velocity of the laser beam to keep the other parameters same like CD. Also, the laser scan velocity is inversely proportional to the omega naught. Why so? Because if the diameter of laser is less and the power is same, please remember, power is same and I am reducing the diameter of the laser beam. Hence, more energy is packed inside this region. That means I can move with a faster velocity if I am having a larger diameter of the laser beam with same power. Then I will go with lesser speed. Also, the laser scan velocity decreases exponentially with the ratio CD by dP. If you really want to increase this ratio, means if you really want to have more value of CD, CD means the depth of the single bead, this depth, if you want to really increase this depth, then you should go slow. It is obvious. And if you want less this depth, you should move fast. Now, if I have an entire bed, wet photopolymer bed, let me try to find out the time required to scan the entire wet photopolymer bed. Assuming that there is no specific cross section to be scanned, the entire bed has to be scanned. So, to obtain that, assume that the length of the bed is capital L and the distance between the two consecutive passes is S. Now the question, why this distance and how much should be this distance, we will discuss when we will discuss about multi-bead scanning. So assume that currently the distance between the two consecutive passes is S and the width of the bed is W. Now if the width of the bed, the wet photopolymer bed is W, then the number of passes will be required N equals to W by S, and hence the total time T required to scan will be N times the time required for scanning the single line. Of course, the time required to scan the single line will be the length of the line divided by Vx. That is the velocity of the beam. We have already got the expression for Vx just now in the previous slide, and I am putting this expression here, and I will be able to get the time T. Here I am writing time T as this expression again. Now usually the distance between the two consecutive passes that is defined by S depends on the diameter of the laser beam, meaning to say the width basically of the bead. If this is for example the beam and this is the width you are obtaining, then the next pass may be this much close only. So this distance S depends on the diameter of the beam. So usually we write it as S equals to K times omega naught, meaning to say if laser beam diameter is omega naught, how much it is overlapping with the next. Okay, so K times omega naught. Now if I am replacing this S equals to K into omega naught, this is the radius. If it is K is 1, that means the step over will be equals to the radius of the beam, and hence I am also replacing the width, the entire width of the bed into multiply by L by the area of the wet photopolymer by A, and hence I have got the expression for time as time equals to A by K root over pi by 2 EC by P naught exponential CD by dP. Of course, now you can see if you want more depth, then of course your time will be very large. You have to go slow with the constant power. If other parameters are same and your power is increasing, then to obtain the same amount of depth of penetration you can move faster. So such observations you can make here to analyze these parameters. You can also see I have replaced the L into W by area, and hence this expression should be valid for any random geometry also if you are scanning it in the passes. Hence you need to just put the area of whatever layer you are scanning to obtain the time.
Now let us try to solve a problem. It is given that a laser beam with Gaussian intensity distribution strikes the resin surface. Its energy got absorbed and exposed energy declined with depth Z according to the Beer-Lambert law. So when it is said that it is a Gaussian intensity distribution, meaning to say it is TEM00, and the energy is also declining along with the depth of into the resin by the Beer-Lambert law. It is further said that the figure shows the experimentally obtained working curve of a UV curable resin called SCR300. Note that the working curve is essentially logarithmic in nature. It means that the curve what you are seeing here is this straight line is between the curing depth CD and the log of Emax. However, if you notice this particular axis, the value written here like 2, 4, 6, 8, 10, these are the values of Emax only. They are not log Emax, and that is why the gap is not consistent. Like here, the gap between 8 and 10 is very small as compared to the gap between 2 and 4. So these values what you are seeing here are corresponding to Emax. Now it is asked that calculate the value of EC, that is the critical exposed energy, and dP, that is nothing but the depth of penetration. So for that, of course, we'll use the formula which we just derived. It says CD is equals to dP ln Emax by EC. I can rewrite this equation in this form and then it will be CD equals to dP ln Emax minus ln EC. Now, if I consider these two particular points where the value of Emax is 40 and the value of Emax is 60, I have extended these lines up to this curve, and correspondingly I'll try to measure the value of CD. The corresponding values of CD approximately are 10 corresponding to 40 value of Emax and 12.3 corresponding to the 60 value of the Emax. Now if we use these two values of these points, one here and another here, then I can find out the two other unknowns in this equation. So let us try to write this equation. The first equation corresponding to this first point, which says the value of CD is 10 when Emax is 40, and hence now we have an equation in dP and EC. Let us try to get another equation corresponding to this point where the value of Emax is 60 and the value of CD is 12.3. Now we have got two equations and there are two unknowns dP and EC. We can easily solve these two equations to obtain the value of these two unknown variables. So for that, we can subtract equation number 1 from equation number 2. As a result, we will be having this equation which says 12.3 minus 8 equals to dP ln 60 minus ln 30. Further, we can find out the value of dP from this equation, and approximately its value is coming to be around 5.67 milli-inch. Of course, if you want, you can convert this value from milli-inch to the mm, and 1 milli-inch will be equals to 0.0254 mm. Further, now utilizing any of these two equations, I can also find out the value of EC. To obtain the value of EC, I'll use, for example, this particular equation and I'll put the value of dP here. As a result, I can easily find out the value of EC, and that is going to be approximately equals to 6.855 millijoule per centimeter square. So this is how you can utilize the available working curves to find out the value of dP and dC for any given resin for the photopolymerization based liquid additive manufacturing system.
So what we have learned from the single bead analysis so far, that for any new resin, we should be able to generate its working curve through the experiment, so that in future, if somebody wants to obtain the property of that particular resin, can be easily obtained through the working curves. Now let us discuss about the multi-bead. Multi-bead means you are scanning one pass and then scanning another pass as well. Hence, as a result, our first objective will be what should be the distance between the two consecutive passes. This is the main goal here. And how do we obtain it basically? So what happened if you are, for example, scanning the first pass and obtaining this particular bead, what you are seeing here, this one. Its width is CW, of course, and the depth or the curing depth is CD. That is the entire depth that is given here, CD. Now, there will be another bead scanned adjacent to it, and this distance between the center line of the two consecutive bead is given here as step over, represented here by S, right? So what you are seeing here is the laser energy exposed in this area will be beyond the critical limit, and this is another scanned area will be the beyond the certain limit, and as a result some additional overlapping of the energy will be here at the center. We will try to obtain the expression for that, but the final bead cure will look something like this. Hence, this much portion as you are seeing here, which I have highlighted here, will remain in the liquid form. It will not get cured, and this is also called as uncured depth, means the distance from this and the bottom or the peak. This particular portion is called as uncured depth. So what should be our objective? Our objective is to keep this uncured depth as minimum as possible, so that your entire layer will be almost flat at the bottom when scanned. So basically the overlapping region will have maximum exposure at Y in and Z in, meaning to say where the two lines are getting intersected. Assuming that the maximum exposure in the hill means this particular region here, this is hill, that is EH, and in the valley, that is here, the exposure is EV, is represented by EV, and hence one can find out the curing depth as the depth CDP, means the curing depth in the peak and the curing depth in the valley. Valley means up to here, meaning to say CDP minus CDV. And of course now you can put these values. So for example, the energy you are giving in the hill is represented by EH, so you know the formula. Depth is defined by CDP in the peak equals to dP, that is the property of material, it will not change, ln E, or the energy given in the peak, divided by the material property EC. In a similar fashion you can find out CD for the valley, and that will be dP ln the energy available in the valley divided by EC. Now if we are writing like this, so you are writing CDP minus CDV, hence you can take dP outside and it will be ln EP by EC minus ln EV by EC. So further simplify it and you can get the expression dP EH by EV. So energy in the hill and energy in the valley. Now our aim is to find out the energy available in the hills and energy available in the valley. Please note that this energy in the hill now may not be the same which we were calculating earlier. This is because, for example, in one pass, this is the energy you are getting. You are exposing this much energy. Now you are overlapping with another bead, right? So in that case, I am considering only this point, right? So that another beam is overlapping this much. If it is overlapping this much energy will also transfer here, and hence your bead width may increase further. So total energy you are exposing at a particular line, maybe I am assuming at the center line, will be even more. And you can see that the maximum energy you are giving will be at the intersection. Now how to find out these intersection points? So for example, this is the curve you are obtaining, z equals to minus ay square plus b, where a is 2 dp by omega naught square and b is equals to dp ln root over 2 by pi p naught divided by vx omega naught ec. Now of course you can rewrite this parabola, equation of parabola, when for the another pass. So this is the first pass, for example, and another pass is at a distance s. So if I am assuming this is the y0, this is the y0, and if I am making another pass at a distance here, so the center distance is s, this distance is s. If this distance is s, I can write the equation of this parabola as z equals to minus a y minus s whole square plus b. Correct? Now I want to obtain these intersection points. It is very easy. You just solve these two equations, and as a result your intersection y int will be equals to s by 2. Okay. So now let us try to find out the energy in this zone. So when can we say that this uncured depth is satisfactory? We usually say the uncuring depth UCD should be less than 5 microns. If it is less than 5 microns, we usually call the condition as planar curing. So The point is, we have already got the expression for under curing depth, and it is coming to be dp ln EH by EV. This expression should be less than 5 micron. If this depth is less than 5 micron, meaning to say you will have a better result. Assume that for a particular resin, I am considering only for a particular resin, the value of dp is 15 into 10 to the power minus 5. In that case, I will have finally, I'll put this value here, and this is for a particular resin I am considering. Please note that EH divided by EV will be less than or equals to 1.034. Now, whenever for different step over, whenever you will obtain this condition, that you can say is my optimal step over. Meaning to say, you can easily write a MATLAB code to observe this condition. So, for example, if this is my first pass, this is my second pass, this is third pass, and so on. Where the energy is maximum, you can easily observe here. The energy is maximum at this location, right? Because here you can see there are 3 times different beams are overlapped, right? Where the energy is greater than the EC, and hence the maximum energy will be in this region. And of course, the minimum energy will be in this region where only 2 beams are overlapping, right? You keeps on reducing this value of EC, more energy will be available, and hence these peaks will become much more in that case. So we have obtained some results from the MATLAB code written for this particular case, and in the end I'll show you also that how you can do the same. So one can easily write a MATLAB code for the same to obtain the optimal step over. So what is the procedure for that? I'll explain in the subsequent slides. Now let us observe here that this is the one pass. Assume that this is my one pass of the laser and give me the maximum energy here. You can see Emax. So I am drawing a curve between E by Emax and Y by W. Meaning to say, what I am doing, this is my expression. If you recall, there is no Z term here because I am assuming Z0 means I am considering just the top surface. It is equals to Emax exponential minus 2y square by omega naught square. In other words, I can write E by Emax equals to exponential minus 2y square by omega naught square. So this curve what you are seeing here is between E by Emax exponential 2. So I can write it like this: E by Emax equals to exponential minus 2 y by omega whole square, right? So this is what you are seeing. This is the curve here plotted. So let me consider a cumulative exposure at point y0. How it can obtain? So before that, let me just find out the maximum exposure at the center line of each pass. So for example, this is the pass at 0, 0. Here the exposure will be exponential minus 2 y by omega naught square, right? So if I go here from here, I can obtain the energy available by this expression. Now for the next pass, this is the another pass. Assume that this is the second pass and I am highlighting it in yellow color. And the distance between this pass and this pass is defined by S. Assume that. Don't just consider this as 1 point something or something. It is some S. Now the exponential, the energy available away from the center of this or with respect to the y-axis available here, the energy will be minus 2 y minus s by omega naught square. And it is obvious the maximum energy will be at y equals to s, meaning to say at this center line, right? And if you go away from this anywhere, the energy will reduce. In a similar fashion, if I just consider another pass which is on the left side, meaning to say at minus s step over, this is the pass and it will give you the energy like this. Hence you can see the maximum energy is at this particular point. when y is minus s. When y is minus s, this term will be 0, hence you will get the maximum energy, of course, because in that case E by E max is nothing but 1, hence E is E max. Therefore, this center pass. So, the energy away from this center pass or at anywhere due to this pass can be expressed by this expression. So, due to this green pass. So, basically what I am saying, energy due to this green pass, energy due to this red pass and energy due to this yellow pass are represented here. But you can write for all other passes as well. So, cumulatively what will happen if I consider any random point. Let me consider a point any in this graph. Let me consider a point maybe here. Assume that this is the point I am considering. So, you can see it will be having the energy due to the green pass, this red pass, this blue pass and all other passes also. We will just add up all the energy available and then we can find out how much total this particular point in the resin got exposed to the laser beam. Okay, so now first let us start with the random point like I have mentioned and I am calling it as y, and as it is on the top of the surface it will be y comma 0, of course. So, this particular point will be called as the energy exposed at a particular point, the cumulative energy exposed at this particular point E y comma 0 equals to the energy exposed due to this, that is E y comma 0, energy exposed by this particular one, this particular pass, that is E y plus s comma 0, then this particular pass E y minus s comma 0 and so on. It will keep on going. We will add all of them. Okay. Now, if I consider not this point at a random location, I am considering just the center one, meaning to say this point, a point here. I am considering a point here. We know that at this point y is 0. So, I can put y 0 in this equation, of course, and hence this point which is at the center will be called as hill point, because you can see that maximum energy is already here and others are also contributing, hence the maximum energy will be here. This is called as EH, energy at hill, right? And energy at valley will be this one. We will calculate that also. So, EH will be equals to when y is 0 and hence y 0 means E 0 0, E 0 plus s, E 0 minus s and so on. Now, let us try to find out the energy in the valley. So, this is the valley and valley point is nothing but the intersection between the two passes. So, this intersection point we have already find out. It is coming at y equals to s by 2 if the step over is s. If the step over is s, the intersection point is at s by 2. That means for this point I can write the energy available in valley equals to Es by 2 comma 0, because what I am doing, I am writing just y as s by 2. Similarly here y is as s by 2, y as s by 2 and everywhere I have just written s by 2. So, this will be the total energy available in the valley and this will be the total energy available in the hill. Now, you can easily do that because you already know the energy expression for energy, right? That is E y comma 0 equals to E max exponential minus 2y square by omega naught square. You need to just put it here, keep on adding for hill and keep on adding for valley, you will obtain the values. It is very easy. Now, if I just draw the cumulative energy in the hill and the valley or anywhere on the surface of the liquid photopolymer bed, I can get different shape of the layer. So, let me just show you when k is equals to 6. So, what is k? Basically, I am assuming s step over equals to k times omega naught, okay, where this omega naught is the radius. K is the, I am considering a numeric value. So, when s is equals to 6 times omega naught means the distance between the two passes are 6 times the radius of the beam. So, this is the beam, this is the radius, another pass will be at some location 6 times away. So, as a result, this is the condition you are getting. So, in the hill, this is the energy and in the valley, you are getting almost 0. Okay, why we are getting almost 0? it is very important phenomena here. Please note that the beam diameter is approximately 100 micron, and I am giving the first pass and the distance between the next pass as 6 times of the beam radius. That will be approximately more than 500 micron. And you have already seen the concept of zone of influence. So, meaning to say your 2 passes are not making any contribution in the energy absorbed by the photopolymer, because the 2 passes are outside the zone of influence. Therefore, you are observing very less amount of energy here. But if this K will reduce, I mean the distance between 2 consecutive passes will reduce, then of course the 2 passes will come into the zone of influence, and hence they will influence the other exposed part of the bead also. Hence, this is the curve you will obtain for K equals to 4. This is the curve you will obtain for K equals to 2.5. This is the curve you will obtain for 1. What you are seeing here, this black color, it is showing the cumulative energy. What you are seeing here in this colorful image, this is the absolute energy. So, it is added up. In the hill, it is added up to this value. In the valley also it is added up, but it will of course will be less than the hill. So, hill valley, you can see that. Now, if I further reduce the value of K, this is the curve I am obtaining. If I am further reducing the value of K, this is the curve I am obtaining. By reducing, this is the curve I am obtaining. You see that it's almost flat, and further reducing, this is the peak I am getting. So, we have to now compromise somewhere and obtain the value of K. You know already that what should be the value of K. So, we will consider the case of K in which the ratio EH by EV is equals to 1.03. Now, there is a question come, how many passes should I consider to find out the ratio EH by EV? Should I consider several passes, or there is a way of reducing it? If you recall, we discussed the phenomena of zone of influence already. So, there is no point in considering the passes those are outside the zone of influence, because the passes those will be outside the zone of influence will not make any contribution in adding the energy to the photopolymer resin. So, just recall this slide which we have discussed earlier as well. This particular exponential term falls off very rapidly with Y, and let me consider the energy when it is becoming 0.0% of its maximum value. Maximum is obviously 1. When this expression will become this much, the Y is coming to be 2.146 of omega naught. Means this is the zone of influence. From minus 2.146 omega naught to 2.146 omega naught. So, if there are several passes, assume that this is pass 1 giving this much energy, then this is pass 2 giving this much energy, this much energy, this much energy. So, there is no point, if I have a point of interest here, if I have a point of interest here, there is no point in considering a pass which is really far away from this. We should consider only the passes those are less than in the range of this much, of 2.14 into omega naught. So, if there are n number of passes coming in this range, we should consider only those passes. Beyond that, we should not consider, because if we will consider, they will add only this much, that is 0.0001. Hence, there is no point in considering such passes. By doing it, you can drastically reduce the calculation time for your for calculating the cumulative energy in hill and valley. Let me just show this slide again. So, my point is, what should be the value of this n, right? Because this n is going to be defined how many number of terms we are considering to find out the energy in hill and energy in valley. So, what is the maximum value for the energy of hill? That is 0 plus ns, right, or 0 minus ns. So, let me consider the ns. So, 0 plus ns is nothing but ns. So, I will consider this ns equals to plus minus 2.146 omega naught. Therefore, your s will be equals to, which I already defined as k into omega naught, and hence I will replace it here, and as a result I will get nk equals to plus minus 2.46. And in other words, I can say the number of passes I should consider can be given by n equals to 2.146 divided by k. If, for example, your k is 1, let me put k as 1 here, then I should consider only the pass minus 2, minus 1, 0, plus 1 and plus 2.
Let us now consider a point of interest as shown here in yellow color, that is corresponding to the energy where hill is available. It has been just derived that only 5 passes are sufficient to find out the energy absorbed by the point which is corresponding to the energy at hill. These 5 passes are shown here. So, in other words, any pass, for example, there is another pass here, 6th pass. For that pass, this particular point which is of our interest will be out of the zone of influence. Hence, we can say that this point is within the zone of influence of these 5 passes only. Hence, to find out the energy absorbed by this point, we can start from this end, that is the energy absorbed by the point due to the first pass, which is shown here in blue color. For this particular pass, which is in the blue color, the point of interest is at 2s distance. Similarly, the next pass which we are considering is shown here in red color. For this particular pass, the point of interest is at s unit distance. The third pass, which is exactly on top of this point of interest at 0, 0, hence we can find out the energy absorbed by this point due to this black color pass. Then the third pass, which is shown here in the yellow color, for this particular pass, the point of interest is at minus s distance. That means it is towards the left side from the center of this pass. The fourth pass, which is shown here in the brown color. For this fourth pass, the point of interest is at minus 2s distance, and hence the energy absorbed by this point corresponding to the fourth pass can be calculated by this particular term. If we add the energy absorbed by this point due to all these 5 passes, that will give us the total energy absorbed by this point, and that is represented here by EH, energy at hill.
As a result, you can easily find out EH will be equals to E max exponential 0 plus exponential minus 2, exponential minus 2 plus exponential minus 8, exponential minus 8, and hence EH by E max will be 1.271. In a similar fashion, you can find out the value of n when we are considering for valley. So, in the valley, the maximum value was s by 2 n plus s. You can see also, once again, this is the maximum value I am obtaining here, s by 2 plus n into s. This is the distance of the point from the interest point, and hence if I just recalculate based on my zone of influence concept, I'll get the value of n as equals to plus minus 2.146 by k minus 1 by 2. If I consider k equals to 1, meaning to say my step over is equals to omega naught. Omega naught is what? Omega naught is your beam radius. In that case, only you have to consider n equals to 1, 0, minus 1, minus 2.
Let us now consider a point of interest shown here as in yellow color. It is corresponding to a point in the valley. The energy absorbed by such a point corresponding to the valley is represented by EV. We have just derived that the energy EV will depend on only these 4 passes. In other words, this particular point of interest will be in the zone of influence of only these 4 passes. If I consider any pass or the 5th pass here, then definitely this point will be outside the zone of influence of that pass. Now we can find out the energy absorbed by this particular point of our interest from different passes. Let us consider first this particular term or the pass corresponding to the this particular term. It is shown here in the black color. So we can see that this particular point which is of our interest is at s by 2 distance from this particular pass. Further, let us consider another point which is here shown in the yellow color. and it is obvious that the point of interest is at minus s by 2 distance from the center line of the yellow color pass. Next, we can consider this particular term, which is correspondingly shown here in the brown color. And obviously again we can see the point of interest, which is in the yellow color, is at minus 3s by 2 distance. Now let us consider this particular pass as well. It is shown here in the red color, and we can see the point of interest, which is the yellow point, is at a distance of 3s by 2 from the center line of this red color pass. The summation of all these energy available for this yellow point will be nothing but the energy absorbed by the points in the valley.
And hence your exposed energy will be exponential minus e by minus 9 by 2, exponential minus 1 by 2, and exponential minus 1 by 2 plus exponential minus 9 by 2. As a result, you will have EV divided by Emax as 1.235. Now you have got both the expression. You have got EH by Emax as 1.271 and you have got EV by Emax as 1.235. Let me now consider the ratio, and now I am dividing EH by EV. So these two equations, those we have just seen, are divided here, and as a ratio I am getting 1.029. Now let us see. So if you recall, we have already seen the ratio EH by EV should be less than 1.034 for the planar condition, and hence it is coming less. That means our planar condition is satisfied. Therefore, S equals to omega naught is the right step over which we can consider for this particular resin which we have considered here. Please note that the whole calculation we did for dP equals to 15 into 10 to the power minus 5. That was the particular resin we considered. Of course, write an easy computer program for that and you can verify this answer with that, and you will find there is no much change. We have considered only few passes. Those were falling inside the zone of influence. Those were not falling or contributing in the zone of influence, we just eliminate them. Now if you can write a code and consider all the passes, and you will find that the answer will not change much. Now we shall discuss a little bit about the multi-layer. You have already seen the single bead. In single bead we have discussed how we get the shape of the bead. It is a parabola, and then we have also seen how we can find out the optimal value of a step over by calculating the cumulative energy at a particular location. Now what should be the layer thickness? Because this will finally define the entire object, and this type of study is called as multi-layer curing. So now multi-layer curing, ideally one should like to have uniform curing throughout the current layer and no curing below the current layer. Meaning to say, if this entire layer is cured, ideally I should be able to cure this much only, then next this much, and next this much. But it doesn't happen. This is because the practice of owing exponentially decay irradiation through the layer depth that follows the Beard-Lambert law. Hence the laser power PL and layer thickness TL are so adjusted to result in curing depth CD larger than the layer thickness TL. The difference, of course, so what we do basically, we slightly cure axis here, and the distance, that is the curing depth CD, for example this is CD, and the layer thickness, that is TL, is called as overcure. So how does it look like? I'll just show you briefly here. So this is the layer thickness finally you are obtaining, TL, and this is the depth of cure for each single pass. You know that this is the depth of cure for the multi-bead in a layer. Now we are giving this excess over cure in the previous layer so that there will be no uncured region. So if you recall, when we were curing in the multi-bead experiment, there was a region which got uncured, right? This we called as undercured region, and it was approximately of 5 micron range, right? 5 micrometer. So what we can do, if we will not cure this region, the liquid will remain here or it may drain out and leave a void behind. So what we can do, we can cure this region by over curing in the multi layers. So this is the first layer we have got. Then I am going to cure another layer. So this is my maybe first layer. Then the next layer or the previous to this layer will be something like this. Or in better picture it is seen here. So this particular portion which was earlier under cured, this one now got cured because of overlapping or over curing of the previous layer into the over curing of the current layer into the previous layer. So this over curing, that is represented by CD minus TL, is approximately 5 microns. So this distance CD minus TL is usually less than 5 microns, so that your uncured region can be accommodated. So with this, thank you very much.